Let's take a look at graphing some polynomials. So in 4.1, we looked at n tendencies and what happens at x-axis at zeros. So we need our degree. This is a 5th degree polynomial. The leading coefficient is negative. So with an odd degree, the ends go in opposite directions. We're up on the negative side. So the edges of our graph are going to look like this. Now we need to find the zeros. So if we set our function equal to 0 and factor, each term has a -3 x cubed that we can pull out. Negative because the first term is negative. So if we take out a -3 and an x cubed, we're left with an x squared for the first term, -4 for the second. If we continue to factor, the parentheses factors to x minus 2, x plus 2. So since we have a product equal to 0, we set each factor equal to 0. So we have 4 unique factors: -3, x, x minus 2, and x plus 2. Remember that the exponent there just tells us how many times that same factor is repeated. So if we set each factor equal to 0, of course, -3 can't be 0. But that one can be 0, that one can be 0, and that one can be 0. So if we solve each of them, this has x by itself, and that factor occurs 3 times, so we would get that 0 3 different times, so it has a multiplicity of 3. For the next one, if we add 2 to both sides, we get x equal 2. Since that factor occurs once, it has a multiplicity of 1. And the last one, we would get -2. Since that factor occurs once, that also has a multiplicity of 1. Remember what multiplicity tells us. If the multiplicity is odd, we cross the x-axis at that 0. Each of these zeros have multiplicities that are odd, so we're going to cross the x-axis at each of those. So if we plot this, then let's plot each of our zeros. We're up on the left side, down on the right side, and we cross at each each 0 at each x-intercept. So we cross here, we turn around, we cross here, we turn around, and we cross there. We're not going to worry about right now how high that goes or how low that goes, because without plugging in quite a few extra points, we're not going to have a good feel for how high the peaks or troughs, how low the troughs are. That's more of a calculus exercise. We just want to know what happens at each of these. Do they touch or cross? And then what happens on the edges? So if we look at another one, this one is factored for us. So to determine the degree, think about if we had the factor x multiplied together 4 times, we would have a degree of 4. Or if we had x times x times x minus 1, that would make x squared. X squared times another factor of x would make x cubed. Now, what about that -1? That doesn't really impact the degree because that doesn't increase our exponent of x. So when we have factors and we want to determine the degree, we just need to see how many x's are multiplied together. So here we have 1, 2, 3, 4 x's that are being multiplied together. If we distributed this, we would have an x squared. When we multiplied it times that, we would have an x cubed, and then another one would give us an x to the 4th. So our degree is 4. The coefficient of each x is an understood +1, so when we multiply all those together, we get a positive leading coefficient. An even degree, positive leading coefficient the edges look like that. So that's what happens on the edges of our graph. Now to determine what happens on the middle of the graph. So we set our function equal to 0 and solve for x. What are the zeros of the function? Because those correspond to x-intercepts. So set each factor equal to 0. So we get x equals 0, we get x equals 1, x equals -5, and x equals 3. Each of those factors occurs one time apiece, so that means each 0 is going to occur one time apiece. So each has a multiplicity of 1. The multiplicities are all odd, so we cross the x-axis at each of the zeros. Remember, odd multiplicity, not odd zeros, but odd multiplicities, we cross at the x-axis. So we have 0, 1, -5, and 3. We're up on both sides, so like this. And then we cross at each x-intercept. So we cross here, and we turn around, we cross here, turn around, cross here, turn around, and cross there. So if you sketched yours, you might made your peak or troughs a little bit higher, a little bit lower, but in general, this is what our graph should look like. On the test, it's not going to be a multiple choice, and I'm going to need to see this work that we got here. How did you determine the degree? How did you determine what happens on the edges? How did you determine the intercepts? How did you determine whether we touch or cross at each intercept? And then we turn that into a graph. Okay, let's do this one. Here, our degree is the 4th degree polynomial. The leading coefficient is positive, so the edges are the same as the last one. So to get our zeros, both terms have a 2 in the bottom of the coefficient, and we have an x cubed in both terms. So if we take a 1/2 out of the first term, that coefficient is gone. If we take x cubed out, we're left with an x. For the next term, if we take a 2 out on bottom, we're left with a 3 on top. And if we take the x cubed out, we're just left with that 3. So we have 1, 2, 3 factors. The one in the middle, that x occurs 3 different times. So if we're looking for the zeros, that can't equal 0. So we said that factor equal to 0, and that factor occurs 3 times. When we set the next factor equal to 0, subtract 3 from both sides, that one occurs 1 time. Both of those are crossing because they have an odd multiplicity. So 0 and -3 are x-intercepts. We're up on both sides, and we cross at both of them. Now we could have other things happen in between there. If we have intercepts here and here, it could be that we have an extra little hump there. We don't really know what's going to happen in between our x-intercepts. All we know is that we cross there and we cross there. Other things could potentially happen in between, but if we have x-intercepts, zeros, that just gives us additional information. It's possible that when our graphs have turns, that they are above or completely below the x-axis, and they would have no zeros. So for extra humps and things like that, we don't exactly know always how many there are. With pre-cal, all we know is what happens on the edges and what happens at our x-intercepts. Here's another one. We have this factor twice, and then we have another factor of x, so two factors with an x, and then another one. That would make a third degree polynomial. Each coefficient of x is 1, positive, so we end up with a positive leading term, leading coefficient, if we were to distribute all of that. Odd, positive, so our end tendencies look like this. Our zeros, if we set our function equal to 0, we would set each factor equal to 0. So we would get x equals 4 as a 0 that has a multiplicity of 2. We would get x equals negative 3 as a 0 of multiplicity 1. Even multiplicity, we touch the x-axis. Odd multiplicity, we cross the x-axis. So let's plot. There's 4, there's negative 3. We're up on this side, down on this side. At negative 3, we cross. So we cross here, we eventually come down. At 4, we touch, so we bounce off of there and go back up. Notice if we were to cross here, then to be going up, we'd eventually have to cross the x-axis again, and that would make another 0. We don't have another 0. So we just bounce off the x-axis at 4. Now, real quickly, the intermediate value theorem says that if we have a function, particularly in this case, a polynomial, polynomials are continuous. Their domain is all real numbers, meaning that when we graph them, there are not going to be any holes or any jumps or anything like that. So we're going to have a continuous function with no breaks in it. So if we know the y value here, and we know the y value here, the intermediate value theorem says that since we have no gaps in our graph, then we have to touch every single y value from here up to here. If there's no place where we have a hole, an asymptote, or anything, then we've touched every possible y value from the bottom one up to the top one, whatever those y values are. So if we plug in -6 and -2, let's see what we get for this function. And for time, I'm probably going to just put these in a calculator. So if I type this in correctly, it looks like we get -44 when we put in a -6. And if we put in a -2, we get -8. Let's see, -2 squared is 4 plus 4, so, or 4 times 4, so 16. -5 times -2 is +10. Then -2, we get 16. So just real quickly, if we just sketch, when x is -6, we're way down at -44. When x is -2, we're up to 16. So -6, -44, -2, 16. So since this is a polynomial, the domain is all real numbers, so there are going to be no gaps in it. So that means when we go from here to the other point, we're not going to ever pick up our pen. So The question is, using the intermediate value theorem, determine, if possible, whether the function has at least one real zero in our interval. So in our interval, this is an x value and this is an x value. So from -6 to -2, from -6 over to -2, does the intermediate value theorem say anything about us having a real zero? Well, yes. If we go all the way from one side, from over here to over here without picking up our pen, we have to cross the x-axis. It's impossible to go from below the x-axis to above it without picking up our pen and not touch the x-axis. So yes. Now it doesn't tell us exactly what that x-intercept is. It just tells us that we have one. So by the intermediate value theorem, we have at least one zero. So by the intermediate value theorem, we have at least one zero. Now let's look at this one. So this interval is going from 3 to 5. So if we plug in a 3, we want to see what we get. And then if we plug in a 5, let's see what we get. So just real quickly, clear this. If we put a 3 in, 3 to the 4th is 81, minus parenthesis 4 times 3 squared, minus 2, so that's 43. And now if we plug a 5 in, we have 5 to the 4th, minus 4 times 5 squared, minus 2, 623. So just a real rough sketch. If 3 is here and 5 is here, when x is 3, we're at 43. When x is 5, we're up in the 600s. Now, what does the intermediate value theorem tell us about a zero? All we know is that we have to touch every y value from there up to there. So does that mean we have a zero? Does it mean we don't have a zero? Or does it mean that we don't really know for sure? Well, let's look at some cases. If we were to go from here to here, we don't ever touch the x-axis, so there are no zeros. But is that the only thing that could happen to go between those 2 points? Well, no. We could go down and back up. Notice that's continuous. We're not told that we can't have points below that line or above that line. All we know is that we do have a point at every y value in between. We could have additional ones if we go down and if maybe we go up past it. Notice we touched all of those points in the middle, but we could also have other y values. We just know at minimum we have to touch these. So we could touch the x-axis, but we might not. So in other words, just using the intermediate value theorem, this is inconclusive. We don't really know if there's a zero or not. Where on the other one, if we were going from down here to up there, we knew we were touching it at least once. We could have gone down some before we crossed, and we could have gone up above it. All we know is that we at least touch everything in between those y values. There is a zero in between those y values, so there's at least one zero. But in this one, there aren't any zeros, or we don't touch zero between those y values, so we don't really know.